Okay, well, welcome to our next lecture on Python. And in this lecture, we're going to be exploring the object-oriented paradigm. And we're going to be looking at concepts such as classes, objects, and inheritance. So we're going to explore how that works in Python. Okay, so that's what's coming up on the menu. We'll start off with the theory itself and explore where that originated, how it differs to other ways of programming that came before it, and then we'll have a look at practically how we can implement these concepts, these ideas of classes and objects in Python. It does look a little bit different to other languages as well, so it's a good opportunity for us to compare how it's expressed and how it's implemented in Python versus the C family and Java too. And then we'll have a look at the concept of inheritance, a core pillar of object-oriented theory, and we'll have a look at how that is worked out in Python. So first of all, let's start with a reminder. Let's remind you about where we have seen classes before in Python. So if you've been following along with the introductory lectures, we've had a look at creating variables, haven't we? So just to remind you, we have a variable, and we've got two in this case. We've got age and name, and they are assigned values. They store values. So we have here an integer, and we have here a string. Okay, and so we assign that using the what we would call the equal sign in maths. We call it the assignment operator in programming. And remember, that assigns what's on the right-hand side to the left. So what we can do is we can assign those values, and then if we wanted to check what data type they are, remember we don't need to assign data types in Python, but if we were interested, we could print them out. And using the type, we can pass those variables to the type function, and that will give us the type that it is. And this is that keyword there, which is what we're getting onto, is class. Okay, so in C family languages, the original C and C++, and I think C# builds them as primitive types as well, in addition to Java. Those primitive types, such as integers, floats, doubles, string usually is built as a class, I should say. That's usually the exception in those languages. Which is an array of characters. Character would be the primitive type there, like a single letter or a symbol or a digit, and then a string is a collection of them. So we have a collection of those single letters, characters, digits to create this array of them, which is built as a class. But you notice here in Python, both the int type and the string, and all the others, by the way, Boolean and floating point number, are built as classes. So that was to remind you that we have seen classes before, but in stealth. So we didn't make a big deal of it at the time because we were focusing more on assigning values, but those are indicators of classes, those types of classes. And so when we have a variable and an implementation of that class, we call that an object. So what we really have here is objects. Objects are just fancy variables, essentially. And we're going to see how we can go and create our own classes and assign. We can create our own classes, and we can implement objects of them. We can instantiate objects of them, and then we'll explore what we can do with them. Okay, so let's get into this. Let's get into classes and objects. Let's look at what they are. Okay, so they are core concepts of the object-oriented paradigm, it's worth saying, and that dates back to the 1980s. So up until that point, you would have had a predominant language like C, or maybe even older, something like Fortran, maybe even BASIC as well before that. These were sort of pre-OO languages, and they operated on this procedural approach, and there's other ones as well, something like functional programming as well, which were known for separating what we call data, you could read that as variables, from the functionality. They called them procedures back in the day, these blocks of code. So that was the previous style, pre-OO, object-oriented programming, was to separate that. But there was opportunities identified for reuse, and that's kind of where C++ gets its name from. When C++ came in probably the early 80s, at that time it was originally known as C with classes, so extended the C language. That's why it's called plus plus, by the way, an iteration of incrementing the original C language, as the plus plus operator is used in those languages, to extend it with classes. So it would actually bundle up a lot of code as a class so that it could be reused. That's one of the key components of the OO paradigm, is being able to reuse content from this class, so we don't have to keep redeclaring it and redefining blocks of code. Okay, so object-oriented programming encapsulates both the data, variables, and procedures, or we could call it functions or methods in other languages. There's lots of different terms we could use. It bundles them up together as an object. So objects are instantiations of classes. We're going to see that in just a moment. And as mentioned, Python does build those primitive types. So, as I said, in other languages, these primitive types are not classes. So we don't get that benefit of having attributes and methods that we can call on variables, let's say instantiations of those types. Whereas with classes, we do. And if you were interested, you could explore the types of variables, the types of methods that you can get in Python with the integers, with strings, with floatables. You can use the dir directory function and look at what it gives you. You should see a long list of methods and variables and attributes and things that you can refer to. So that's basically just saying that we do have things that we can access as part of those types there. So that's sort of the background to the context of object-oriented programming. The paradigm sort of originated back in the 1980s and has stayed pretty much the predominant form of, predominant style of programming since then. So that's definitely worth getting on board with with our Python coding. So let's explore the key difference between a class and an object. And I've got here some pictures here to try and illustrate how we can kind of get our heads around what a class is. So picture yourself on a building site, and let's imagine we're in the construction domain. Well, we don't just first of all just jump straight into a building site and just start building any old property or building. First of all, there's planning that goes on, isn't there? The architects, they all get around a big table and they start drawing things. They start drawing out these big maps, don't they, of what the room layout is like, where the stairs are going to go, where the doors are going to go, how long the walls are, where the fire escapes are, or different levels of the buildings. They go to town, don't they? They really put a lot of energy and effort into mapping out exactly how this building is going to look. The construction workers don't just rock up and just do whatever they feel like. They're building to a plan, and that plan we could call a blueprint. So, obviously in the architectural world, it's called a blueprint. And the constructors will build to that specification. It's all mapped out first of all, and they just build, and what this shows here is that they can build multiple properties to that specification. It's not a once-only deal for building a whole street of houses, whilst they obviously have a unique address number, and they might have different colours, they might have different variations on them, where the windows go, you might flip around maybe with the doors in some locations. Whatever the slight variation is, the key thing is that design, that blueprint, can be reused. It can be instantiated multiple times to create, in programming speak, we call those objects. So we can build objects, or read fancy variables, you could say, variables with multiple components, from that design. So the idea with programming is that we define classes which allow us to instantiate multiple objects from that class. They're all unique, of course. We can give them unique features, unique attribute values, and We can reuse the methods that are defined, those functions that are defined within the class. So we kind of get the best of both worlds. We've got the reuse aspect from defining it once in the class, but we call those functions on unique objects to affect their values in a unique way. And this is a housing example, obviously. There's lots and lots of different metaphors and different examples that we can use. And that's exactly the point, actually. That's exactly why it's found so much favour with programmers, is that it models the real world, in that we can model entities, such as buildings, devices, even people, students, staff. Even in game context, you could have a whole army of zombies or orcs or whatever the context is. We can model stuff that we would be having to write or code a lot of. The idea is we write it once, we define a blueprint, a design, and then we just create multiple instances of that, which are unique and can have their values set accordingly. So that's the theory behind the classes and the objects there. I think most of our examples were modelled on the student context, because that's exactly the type of domain we're in right now. So I thought it'd be good to give you something that you can relate to. So that's what we're going to see going ahead. But you can apply the general concept. The abstract idea, of course, these are ideas. They're just concepts that we're thinking of. We're going to translate that into implementation. We're going to realise that idea. And another key thing to remember about classes is that they define or would define two components usually. Other than the class name, the entity name that we define it to have, they would typically bundle up, as we saw, variables, so data. There's lots of terms that we can use for that. Storage of characteristics, attributes, for like students, their name, their ID number, the modules that they take, for example, things that each student would typically do. And then, of course, behaviour, functions, blocks of code, verbs, things that students could do or any entity could do. So they could attend lectures, they could submit assignments, they could see their scores and their marks, etc. Get to print out a transcript. So that's usually what classes describe. And as mentioned, there are lots and lots of different terms, depending on which books you read, depending on which language you come from, that could describe these terms. So I've tried to list a few of them so you can see them. So variables, we've seen those before, otherwise known as data or properties or attributes or characteristics. There's loads of them. Either way, they are just storage locations that can store typically single values. And are built as part of the class. They describe the characteristics of an entity, like we just said. And then functions, so behaviour, methods, subroutines from older languages as well. Things that someone does, or an entity does, like we just mentioned in terms of what a student could do, or what a building might do, or what sort of behaviour there is to an entity. So that's usually what's modelled in these classes, and we're going to see how we implement them. Okay, so there's lots and lots of different terms that could be used interchangeably. Some would say that a function that's defined outside of a class in Python is called a function, but then as soon as you define a block of code in a class, it's called a method. Even though it looks pretty much the same, does pretty much the same thing, it just takes on a different meaning because it's a method of a class rather than just a standalone function. So there's lots of different nuances and different ways you could look at this. But anyway, I just like to show all the different terms just so that you can try and equate them. I know it can be confusing when lots of different terms are used, so I will try and stick to try and minimise that number of variations that I give. I'll try and stick to variables and functions if I can, just so that you're going to follow along. Okay, so that's the key thing there. Just to remind you again, just to summarise this, that classes define the blueprint, they define the design, and we have to first define the class before we can instantiate them. So we have to define exactly what it is that makes a student, or makes a house. Like I said, the architects will get round the table, they'll sketch it all out before a construction worker even sets foot on the site. This is way before that. They're going to design it all out, they're going to think about the design and prepare it ready. Once it's finalised, only then is it then built. So we have to define the classes first and in our code, and then we instantiate them. That's a key word there, that objects are instances of classes, and we instantiate the class to create an object, or a fancy variable if you prefer. And that can be assigned unique values, and it can reuse the methods, the functions that are defined in our class. Okay, so that's the theory. Let's have a look at how that is implemented. So let's start you off with something that's hopefully going to be fairly small in scope, something that hopefully we can get our head around. So we see both here. We actually see the definition of the class, and then we're going to have a look at how the object is created. Okay, so let's start with just focusing on the class. So keyword is class, self-explanatory. We're defining this is a class. We don't have to use the def keyword. We can use that within our functions, methods if you prefer, but we just state class, and then the class name. So we give it a name. Conventional to use uppercase, that's used across all the C family languages and indeed Java. I believe it's that way in Python. As with most things in Python, we use the colon there. We don't explicitly need a pair of parentheses. We could do when we get into inheritance, that's coming a little bit later. But right now, we can just write this. We can just write class, and then give it an entity name student. So we're trying to model the student entity. Remember, we're setting this up long before we create the objects. So what typical things do students have? We can think that through. What typical behaviours do students perform? We can think that through. I've just got a very small example here. It's very simple. Just print the name. So students could see their name, for example. So this is a function that sits inside the class. And if you read down to there, we haven't actually got an opening and a closing code brace like we would in other languages, the more statically typed ones. But the indentation is quite important, so we can tell that we've finished the class when we come down to the object definition. So we're defining this function, print name, and then it's a function, so we know it's got a pair of curly brackets, parentheses. Now, we're going to come back to self. That's going to be quite key to Python. We're going to come back to that, but we'd have to write that as a reference to the object, so that it knows which object it's dealing with. I'll explain more about that in just a second, but that's a new addition. But it's a function, regardless of whether we declare it inside a class or outside a class. So the functions, it's a block of code, so we need the colon. And then what's it going to do? It's just going to print. Nice and simple, just to get us started. It's just going to print this message, hi Nick. Okay, so it's a function that's declared inside this student class, this student entity. So that's our blueprint, okay? Now, what are we going to do with that? Well, we're going to instantiate it. And to do so, to create an instance of this blueprint, remember we could create multiple of them, we've got some examples as well to show you how to do that. We call a special method, a special function. It's called the constructor. And again, there's more to come on that, but just for now, you notice here that it's a function, method you could say, it's got a pair of parentheses. So parentheses are usually a giveaway that it's a function of some kind, a block of code. And you notice that this student reference is actually, it's got a capital, so it refers to the student class name. Giveaway is the capital letter. Pretty much everything else has got lowercase. So uppercase, first letter for classes. So method of the same name as the class, so that's typically known as the constructor. I haven't actually defined the constructor in here, and we're going to get into a special way to do that in Python. But what it does is it's going to return a reference which I'm going to assign. Notice the equal sign, the assignment operator, just like we would for standard variables. we would say name equals Nick and age equals 30. We've got the same thing here. We're going to return a value, a reference, an object reference, and a memory address. Got an example to show you that. And I'm going to assign it to this, well, I've called it obj for objects. You could also call it a variable, a fancy variable. So I have a variable of this type, just like you had variables of your integer types, your string types, your Boolean types. Same thing, I've just defined what type now. I've got a custom type, custom class called student. So that objects, variables of this type are of that sort of structure, let's say, so that I can refer to methods of that structure and attributes of that structure. We've only got one method so far, print name, which I think I'm going to call next. Yes, so on that object, notice the dot notation. That's again key for OO programming. I'm going to refer to that on a specific objects. So again, it's not just any random object or anywhere else in the code. It is this specific instance of that class that I'm going to call print name on. And you'll see an example where we have multiple and we call the same method. We have multiple objects and we call the same method, and you'll see that I'm going to call print name on each one. I'm going to reuse this structure. So we call print name on that object, and what do we get? We call it, and we should then see this statement. Hi Nick. There we go. So I called that block of code on that object, and we've got the return. Hi Nick. So trusting that makes sense. That's a reasonably small scope. Just to illustrate what the object looks like, let's have a look at what we see when we print it out. So we can actually just print it out directly. I'm not calling this method here, I'm just printing out what is stored in obj, which, as I said, we actually get a reference returned. We've got this hexadecimal address here. We've got a student type, an object of student type, at this memory address. So that's what's actually returned, and the location in memory that is returned by the call of the constructor, which hasn't actually been defined yet. We're going to come to that. Okay, so that's what's actually stored there. And then remember when I call the dot, when I use that dot notation, that can be used to refer to another function on that memory address. Okay, so let's show you two now. This might help illustrate exactly how we can reuse that structure to create multiple instances of that class structure. So notice now I've got two constructor calls. I've got one here, so I've kept the same definition of the class. And I've rebranded it now, so obj, I've rebranded that to Nick, a specific student. And I'm going to call the constructor to return one reference, and then print it out, you can see it in a moment. And then another object, I'm going to call the constructor again, so it's the same method, I'm going to call it once again, and then return another reference at Sam, another student. Okay, so let's print both of them. You'll see, we kept the original memory address, but then we've got a different one for the second object. Okay, so two different memory addresses, but they're of the same structure, the same type. Okay, that's going to be quite important going forward. And here we go. Here's that illustration just to show you that I can call the same method on two different objects. In this case, we're going to get an issue though, because I've got two objects, one's called Nick, one's called Sam, but because I've only defined hi Nick in the contents of this function, I'm going to get that twice, when really I guess I was hoping to see hi Sam. So we're going to explore a way to amend the code so that we can do that. But hopefully this just illustrates that I can reuse that function on multiple objects. That's key for object-oriented programming. I don't have to define two print functions. I can have one, and I can call it for how many other objects I have. I can reuse the logic of that. Obviously, I'm going to want to customize it so that I get a different message based on the object I'm dealing with. That's exactly what we're going to do. But it does illustrate that dot notation that I can call the print name on that particular object. And in the next few slides, we're going to get a different result. So let's explore that. What can we do to change this code? Let's look at the self-reference. So I shared it previously. We're going to explore it a bit more now. Otherwise known as this in the C family languages and also in Java, self is the rebranded version of that in Python. And it plays quite an important role, actually. It plays a number of different functions because, first of all, self is a placeholder for any given object of the class. And that's quite important because remember, when we're defining the class, remember we do that well before we create the objects. So just like the architects gather around the table and they draw up the design, there's no houses built yet from that. So they have to, well, in our case, in our programming case, we have to put placeholders for something that's going to come in the future. So we haven't got the objects yet, they're coming in the future, so we're going to have to build in sort of placeholders, things that can then be substituted for concrete references to be defined at a later stage, okay? So it gets around the problem of not having a specific hard-coded created object name that we can refer to at the point in which we create the class, okay? And furthermore, it can be interchanged for multiple objects of the class. It can be switched between. So again, we run the risk of if we were coding it in a hard-coded way, where we actually define exactly which object we're going to refer to, that could never be changed. Think back to this. This is hard-coded, it's set. I'm not going to be able to change that. Hence why I see Heineck twice. So we want to code in a way that this could be replaced later. So that's where self comes in. Self can allow us to refer to another object at the point in which we call it, okay? And something in Python that's quite specific is that it's passed implicitly, okay? We don't have to explicitly pass it. If you were to play around in the code and you were to say try passing in some variables, it would tell you if you had a mismatch of data that you're passing in. Okay, so when we look at this and when we unpack it, you'll see here that I have I'm passing in data now. Let's just have a look at this example. We've got the student class set up. And what I've changed about it is that we've now got an extra variable added into the parentheses of this function being defined. So it was before, it was just self. Now it's self and name. Okay, but notice here, no self is being passed there. That's being passed implicitly. I don't have to manually write self there. Indeed, self doesn't even exist in this context. It exists in that context, the context of a class. So, as I say before, if you're from other languages, the two would have to match. The number of parameters to be received would have to match the number of parameters to be passed. But here it isn't, okay? So, self's being passed implicitly. That was the point there. Let's have a look at what we're doing here now. So, as I said, we've defined the class. As we see before, we've changed these bits, we've added name. And the idea here is another function of self, is that we can also refer to attributes of the entity. And something that's quite different about Python is that we're not declaring these class attributes above. In other languages we would define the variables that are part of the class just above the functions, just underneath the class declaration, and also just above the definition of the functions. But we don't do that in Python. We actually use sort of self-contained. It's part of the self here. So the self holds that variable, that name attribute. Okay. So that it performs another function. Self's very, very helpful. It does an awful lot. So let's have a look at this. How do we do this? So we've got we've got the constructor call again. That's something we will get to. That returns a reference. We've seen what that looks like. I've rebranded it to Nick. I've got a more concrete student now, and that gives us a reference. When I progress on to the next line, remember I'm not passing in self and the value for Nick. I'm just passing in the value for Nick, and that's going to go into name. Self's taken care of. We don't need to worry about that. So the name Nick's going to go to there. I'm passing that value to that function on the Nick object. So the Nick's name is going to be set to that value. So it's not for any odd object, it's for the object of Nick. And that reference, the memory address is where the self is going to come in. So it's that bit where it's not just any old object, it's the reference for Nick. It's Nick's object. The name is going to be set by that line. Okay, so name referring to what we pass in, and self.name referring to the object's name. It's another point of confusion because we've got two name attributes, haven't we? Two variables called name. Which one's which? Well, we can distinguish them by self very handily and have a use of it. So we refer to the object's name as opposed to the local name, which is just being defined up above and is literally a placeholder for this value being passed in. Okay, so the idea is really just to pass it to there and then to set it to the object's name, for Nick in this case. And another feature of Python is that, again, when back in other languages we would declare the scope of these class attributes. We might make them private or public or protected. Here in Python, we sort of assume that they're public because we can refer directly to them. If they were set to be private, we wouldn't be able to. So whilst we don't even worry about scope in Python, we can assume it's a public scope because I can refer directly to it rather than having to call a getter method or some sort of other method to return the value of a private attribute, sort of self-contained within students. So I can actually just print that directly, refer to the name attributes. Remember, that's a placeholder for Nick. So now that I've set it, hopefully, through this function call, I can refer to it. What's the value of the name attribute on the Nick object? Well, it's logically what I set it to be, Nick in this case. So we've got a little bit more flow now. So we're sort of scaling up the complexity, a little bit more to go as well. I hope that's making sense. It's also a little bit abstract because self, it's not a concrete term. It's a placeholder to be substituted with later. But like I said, it fulfills a number of different uses because we can write it at the point in which we don't have objects declared, and we can also use it to distinguish between attributes of the same name, same semantic type, so we know exactly which one's which. We know that this name, which is part of self, and remember the dot notation there, refers to self's name or the object's name, whereas name without that is going to refer to the local attribute called name, which really is a placeholder for that value being passed in. Okay. We've got another example here, just again to expand that, just to build on that previous example we saw. Remember when I had print hi Nick twice? We want to change that, we want to amend that now so that we pass in a unique name for each object, and we've got code that can do that now. So we extend that further to be able to set each object's name by passing in a unique value. We reuse, no, I haven't got the example, that's fine. We reuse the set name function, but self first takes on the memory address of the Nick object and sets its name. And then when we come down to create another object, another memory address, another reference, we use that as a placeholder, self, so we set the name attribute for that object. So we have two objects and we've reused self. We have changed where it's pointing to, which memory address it points to, so that it can set the a name attribute for that. Even the name attribute's the same, because we've defined that as part of our class. We say each student has a name attribute, but each student object has a unique value. So it's the same structure, just has a different value depending on which object it is. Okay, so hopefully you're still tracking with me. We are scaling up the complexity now. Let's have a look at the constructor in a little bit more detail. We've seen self, and we're going to see self again built into the constructor. But to take it another step further, let's look at what the constructor does. Well, we've seen a few things already. We've seen that it has the same name as the class. You saw that previously, didn't you? So my class name was student, and a method of the same name as the class, which is student, is the constructor. It's typically the first method that's called. We would do this in all the other languages as well. Even though there's other things appended to it, it's still the same. It's still a method of the same name as the class. That's the same in Python. However, it translates slightly differently at the sort of defining end, where we actually write the constructor. Because in Python, we refer to what's known as a dunder method. And that dunder method is an acronym for double underscore. Put the D and the under together to get dunder. Okay, that's where you see these two blank lines there. Two underscores that come together. In this font there isn't a space in between them, so you can't tell. But they are two underscores together. And init, short for initialization, not street talk. It's short for the initialization, okay, not init. It's short for initialization, as we see here. All right, and it's a method. We know it's a function, because it's got a pair of parentheses. And that, well, what happens is when we call the constructor of the entity name, like student, the Python interpreter actually goes back to call this method. Interesting. It's a method that's part of the class, a higher class, let's say. And part of the Python interpreter can call this method to then enact the functionality of the constructor. So we don't call the constructor directly. It actually routes through to call this init method. And what we can do is we can basically override that. We can override the functionality of this base init method, which, if in our previous examples we didn't have that, so it would have just left it as it was. It wouldn't have overridden the core, the default code in the init method. Basically, I presume all that does is just create the initialize the memory address, which we then see, and that's what it returns. Don't we? We saw that printed out. But what we can do is we can actually override this to have more functionality. We can add things to it. So that's exactly what we're going to do now, is we're going to define our own custom version of this init method. Okay, so here's what it is. I've removed the print name. I've removed the print name function, and instead we've got a custom version of init. And that takes the self reference, so that's exactly as we saw it before. And it also takes the name attribute. So again, that's an appropriate place, is the constructor, to actually initialize values for variables, attributes of our classes, objects of those classes. Okay. So I've just repositioned where this is going to be set. I could have a set name function that goes along with this, but just to illustrate what init does, I thought I'd rebrand it to that so you can see it. Okay, so it's going to perform exactly the same thing. The only difference here is I haven't got an explicit function call where it sets the name, and we're going to build it into the constructor. So again, contrast this with what we saw previously. Nothing was being passed in to the constructor call there, because we haven't changed it. We were actually passing that value to a different function called setName. But in this example, we are going to pass the name to the constructor directly. And remember, the Python interpreter will route through to this method, because we don't have the students written here. We don't have the constructor of the student name, which is a bit confusing in other languages we do, and it kind of makes sense because you've set up a function which relates directly to it, but the Python interpreter will interpret this to refer to the init function here, which acts as our constructor, initializes it. So we're doing the same thing again. We're passing in the name. That's going to be set to the name attribute of that particular object. Remember, that's passed implicitly, so that goes into self. So it is Nick's name. That's going to be set to name. And then again, we can just print it out. So in actual fact, we're doing very similar things, but we've just changed the means by which we do it now. Okay, so we're still utilizing self. Rather than it being in a separate function like set name, we're going to utilize the constructor. Like I said, there may be reasons to have both. You may want to set it in the constructor to start with, and then deliberately you may want to change it later. That's also quite common, and that goes far beyond the name attribute. You could do that for marks, for example, updating marks. You might set it, you might initialize it to 0 in the constructor, just when you're setting up the objects at the start of the term. But obviously later as we go, as we give you marks, we want to update it. So we want to update the marks attributes for each student. Okay, so that's just the means by which we have that constructor functionality in Python. Okay, so there's a little bit of things to get our head around there. We've got a lot of flow now. We're passing things back and forth a lot, so that's where things start to get a little bit more complex. But hopefully these simple examples are just showing you how we could use those object-oriented concepts in a very small example. Okay, so just step it through bit by bit, and you'll be able to trace it through and how it goes. Okay, so that's the constructor. And also, it's worth mentioning, in other languages we can overload the constructor. Java, the C family, but in Python we can't. So we've only got one. We've only got one constructor. However, we can have, let's say, derived classes. We're going to get into that in inheritance. But we can have other constructors. They're just of a different class, and they perform another function. I think that's what's coming up shortly. Okay, but just to move on, let's illustrate how we could just do this again with two objects. So we've done it already with a Nick object. I'm going to pass that into the constructor. Remember, constructor is the function, the same name as the class. Python interprets that to mean this. Oh, you mean init. Okay, we're going to call that. We're going to pass it there. For which object works for Nick because it's that particular reference. So for that attribute, assign it Nick to start with, and you see that. And then we've got another object, so we have another memory address, and assign its name attribute to be Sam, which is what we see here. Okay, so again, hopefully reasonably simple. We're obviously classes will scale up to have far more methods, far more functions than just this, but we're just trying to constrain the scope just to make it a little bit easier to get a handle on as we're starting out. Okay, so there we go. That's how the init and the self can be used for two objects. Okay, so let's move on now. Let's take it a step further. Let's look at inheritance. Okay, so we're slowly building up in our scope. How does inheritance work out? Well, first of all, let's just remind ourselves, what is inheritance? So obviously, in our social world, we might refer to inheritance as the passing down of assets, of wealth, of other resources, from generation to generation. Indeed, we inherit our parents' DNA when we're born, of course. So children, typically in our world, and animals and mammals, will inherit features, assets, DNA from their parents. Okay, so we model that concept in programming. We can have classes which inherit from other classes. And that typically allows us to specialize now. We can have a generic entity, such as student, and then we can have specialized versions of student. Well, we might have a part-time student. We might have an undergraduate student. We might have a postgraduate student. We might have an associate student. We might have a PhD student. Okay, if they have enough specialisms, they have enough attributes that distinguish them, well, we could build unique class types to model that. Okay, so Again, there's multiple terms by which these different levels go by. You might go by the terms of parent and child. So obviously the specialised classes inherit from the parent. There's other terms as well. We've got a slide on that very soon, such as base and derived, and then super and sub. But the idea is that the children specialise, or might be known as extend in our language. They extend the parents. Okay. Here's that slide on the different terms. This is using UML, Unified Modelling Language, the arrows from that. So in the design context, think back to the architects where they get on the big table and they draw everything out before. Okay, so if you were doing that, if you were drawing out a big class diagram with all your different classes that you plan to implement, you might have something looking a bit like this with the arrow. Okay, so it's typical that the child or the derived or the subclasses, different terms again, just like variables and methods, depends on which book you read, they will inherit from the parent, the base, or the superclasses. Okay. I personally like the parent and child, probably because I'm human, and I can refer to that. But there are lots of other terms, base and derived, probably a bit more mathematical, derivatives, and then super and sub as well. That comes from other languages, and indeed we're going to see that the super reference is going to be very important as a keyword that we're going to use in Python. So that's the concept. The child, the derived, and the sub inherit from and extend and specialise the parents. So they can inherit variables, they can inherit methods as well, they can refer to that. Saves us having to redefine that same functionality or the attributes. If both a part-time student and a student, they both have names, well, rather than having to keep redeclaring name all the time, we can just have it in the student and then get the part-time student to refer to it, to, in other words, inherit it. Okay, and then what they do is they extend it further. They add on additional features. The part-time student adds on additional features. Okay, so as we've seen a few times already, it's expressed quite differently in other languages. So inheritance in Java, that keyword extends is how it's implemented. So that we see written in the class definition that the child class extends the parent class. C languages, C, C++, C sharp, use the colon. So different meaning to the colon in Python. In the C family languages, they have child class colon, parent class. But in Python, we have another way of doing it. Let's have a look at it. We've got this instead. Not the colon, different meaning here, and not extends. We actually now have put the parentheses back in. Notice we didn't see that before with our single classes. Now we have. We've put it back in and we've put a reference to the parent class name in there. So that objects created of this class will inherit from objects of the parent class. Okay, so here what I've done is I've got two methods. One's called print name in the parent class, and the other one's called print new name. And it's quite deliberate, just to help you distinguish between them. So they're separate methods in two different classes. Okay, so this one, just again, to give us a cue. Well, this one is high from the parent class because it's declared in the parent class, and this one's high from the child class because it's in the child class. But what am I going to do? I'm going to create an object of child down here. Whenever child constructor, return a reference, store it in child objects, and which method am I going to call? Print name. Now, does that reside in the child class or the parent class? It resides in the parent class, doesn't it? Print name. So that allows me then to call something that I've inherited. I can call print new name as well, but I'm going to call print new name just to illustrate how it works. And here we go. We've got the steps through of how to do that. Like I said, we have the reference, and then we call print new name to refer to this one, not this one. I could refer to it as well, but I've got access to both because we're inheriting from the parents. Okay, so I think we're going to take this further and Yes, look at the super. Let's look at how we can take this another step further. So super, let's have a look at that. So that is a reference back to Java, actually. In C family languages, I think it's referred to as base. Okay, just to distinguish. But we're aligning ourselves with Java in Python, the super reference. And it's got equivalence, because self, we've seen that as a placeholder for the just one single class. It refers to an object of that class, whereas super is a reference to the parent class. So you could read as self as a reference to the single class, or it can still also be used to refer to a parent class if it's used in that context. But super is the level up where it refers, if you're in the child, it refers to the parent's class. Okay, and it's just a shortcut to enable us to be able to reference. We can use it to reference the parent's constructor, because guess what? It's a function with the same name as the class. If we said that is a placeholder for the parent, we can use that to get access to the parent's constructor. Or in Python, we route through to the initialization function, don't we? Okay, and we can also use super to refer to particular attributes. We've already seen that they're public in Python, and we can call out functions too through the super reference. So that's really useful, actually. And I think here we've got an example of that. Yes. So now I have changed the function name in the child. So remember, it was print new name. Here it's just print name, exactly the same as print name in our parents to illustrate points. Okay, so first of all, we define those classes, and what's key about this is that we have the super reference. What does that refer to? Refers to the parent class, because remember we're inheriting. That's still the same. We've still got that in the child class, and then we refer to the parent's print name, so that once we get the reference of the child, and we call the print name on the child, we route through to call the parents. There it is. We route through to call the parents' print name, because it's being called on the super. Okay, so it can enable us to call that. And usually what happens is the child, once it's called the base, kind of the default, print out whatever it's doing, it then extends it. Often you'll see code underneath or above which will add extra things to this sort of default or base message, let's say. And again, that saves us having to have the same message multiple times. We can customize it and only change certain parts of it. Okay, we don't have to have the whole thing duplicated across lots and lots of different classes. So that's very useful to be able to do that, actually. So that full thing would then print out, obviously, the hyphen parent class, even though we started with the child. And that's another thing, of course, because we have here, I guess you could say overriding, and we probably would say it's overriding, and we've got two methods of the same name. So because we inherit from this, well, which one do we choose? Because they're both the same name. If we've got access to both of them, because of precedence, that's the same in other languages, we would opt to prefer the child. Specializes, doesn't it? Specializes the parents one. So there are ways in C++ you can actually refer to the parent directly, use of virtual functions, vtables as well. But here we're going to start, at least by default, with the child's one. But notice here, that super reference allows me to go back to this one. Okay, so again, flow again. We go lots of different places, lots of different locations in the code. We start here, go to there, and then to there to get that coming back. Okay, so we've got to trace it through, we've got to look at it slowly again. I think we've got one more extension to go. So let's build in now the constructors into, and I've got some very specific names now as well. I've got, rather than parent and child, I'm going to put some concrete terms to this. So student as the parent, it's general, and then a specialization of that student, which is part-time. Okay. add in what we've looked at previously with the constructor. We've got self again, remember, that's a key part of this. And let's try and break this down. So, where do we start? Well, we call the constructor part-time student. So we root through, the Python interpreter says, you meant the initialization function, we call that. So we override that default one with this one. And we pass in, remember, an implicit reference to self, which is the memory address that it's going to create. And we're passing in a unique name, a string value for this part-time student. So that's going into there. Where does it go from there, though? It goes up to here, doesn't it? Because we call super. We call the super, the parent student, we call its constructor. Called in it. You meant that. I'm actually saying quite explicitly, aren't we, here? We're not saying the name of the class entity, like student, we're calling explicitly the init, the initialization function. And what are we passing? Passing in name. Okay, we don't have to pass self, that's passed implicitly. So for the student's name, this is an attribute declared in the student, part of the student, okay, out of this self reference. We're going to pass this all the way to there. It's going via the here. So we pass it to the constructor of the part-time student, and it's then going up to here, and it's being set for that reference. Remember, that's a placeholder, whatever this is going to refer to, so that when that reference is returned, I can then refer to the name attributes of a part-time student. But notice it wasn't assigned in there. It wasn't assigned in the part-time student. It was assigned in the student. It's an attribute of the student, part of the self-identity of the student. So that enables me to then print it out. It saves me having to repeat the declaration of name within the part-time student. The idea would be that the part-time student could add on additional features and additional functionality to the generic student, which enables me to continue creating objects of the student, which obviously have a name. I don't want to remove the name from student, because that's going to affect objects which are just of the generic entity students. Okay. There are other things known as abstract classes where you might want to do that. You might not want to have an object of the generic class, the general class. You might want to deliberately restrict that in the case of, if you had the example of like a shape, and shape was the parent class, and then you had specific implementations of shapes like triangle, square, circle, ellipse, oval, etc. We don't just have a general shape, have a very specific implementation of that. The same way as what we might do as animals. We don't just have a generic animal, we have a very specialized version of an animal, like a dog, or a cat, or a zebra. We don't just see a general blob walking around that's just known as animal. We have a very specific instance of it, like as I said, a dog or a cat or a zebra. Okay, so there we go. In this case, we have used we've used a lot of things. We've used the constructor, we've used the self, we've used the super, and we've got very specific names for them. Have we got one more? Yes, we have got one more example, I think, which is where we're going to keep that functionality we had in the previous slides, but we're going to add on another point of data, 6 here, referring to, I think, 6 hours. So let's break this down. Let's look at the first one. So the first value, Nick, well, that's still being set in the parents constructor. It's still an attribute of the parent class, the general class, which is students. So that's still going to be routed through. Remember, it starts in the child classes, the part-time students constructor, and it's then sent to the initialization function of the parent class, which is here, set there. So Nick's still being set to the name attribute there, okay, as we saw in the previous slide. But now we've got another approach. So for the 6, if this was an extension, i.e. if part-time student added this feature, this variable, which wasn't present in student. Well, I can't just send it to the student because it doesn't exist in that context. The part-time student has added this. It has extended it to have this. So therefore, this variable, this value, has to be set in the child class. Remember, the first attribute was set in the parent class, the student. So it's routed through to there, and set there. But this value is set in the child class, underneath that super cool, okay? So here is where we have that same format of self, so the memory reference, its hours are going to be set to this value that we pass in, which should be in there as well. We should have a comma there to say that's being passed in to here, so that we can then set it, okay, in that place. So there's a lot going on there with this example. We've combined a number of different features now to be able to make classes and objects. We've got classes here. We've seen objects, we've seen the constructor calls, we've seen self, we've seen super, we've seen an awful lot of things coming together. And these, I should say, are pretty small in terms of the scope. We can also extend these to have much more in terms of attributes. We've only had a few here. And also methods. We can have a lot more methods, not just the constructors and setters. We can have lots of prints, lots of other functionality that we can utilize in in our classes. So that actually brings us to the end of the lecture. There's a little instruction for you. Have a go at some of the exercises to see how that works.